I'm between you and lunch, and the Java memory model as well, which is dangerous. Okay, so we've all seen this slide before. Don't place bets on what I say. So I'm going to talk about atomic VarHandles that both John and Brian talked about, and it really it's three things here. So it's a reference to an underlying variable wherever it resides in memory to safely perform atomic operations on. It's motivated by JEP 193 enhanced volatiles. It's online, you can read about it. And it's inspired very heavily by method handles. So the current situation is we have in Java at the moment, there's a bunch of fields that are volatile. Like Brian said, we can't, if they're volatile, we can't access them relaxed. There's some misc unsafe that we have, and we have these atomic classes. So it's a whole bunch of mixed stuff we have there. And there's the bad and the ugly. The atomic classes have a bit of overhead. I think Duncan talked about the atomic overhead he had when he was using classes there. And they're not used in Java util concurrent. We don't actually use our own classes there because we're not happy with the performance of them. And also, some misc unsafe is, well, unsafe by its name. It's not portable, and it's going away. And something like compare and set is just too important to relegate to unsafe. We need to uplift it up and put it properly into the language, which is performant and safe. And essentially no unified safe model for accessing on and off heap data. So this is what we're going to try and solve. So just a bit more about the unsafe situation. I have some slides pointed to here which talks about it a bit more. When I say unsafe is going away, it's not actually going away, but we'll make it so that it's not, actually that's a mistake. It should be made not accessible, because Jigsaw will enforce strict module boundaries, so it's not going to be accessible to people in Java 9. And there's a bunch of vertical use cases that you use unsafe for. When you can peek and poke at memory, you can do anything you like, and people do the crazy stuff with unsafe, and some impressive crazy stuff too. But we can tackle a bunch of these vertical cases. You saw some of these already with Project Panama and Project Valhalla. They actually tackle some of these cases where people use unsafe today. And one of these vertical cases they have, what we're talking about is JEP 193 enhanced volatiles. It tackles one such vertical case in a particularly more narrow case than in Valhalla and Panama do, but it definitely tackles this case. So what we want here with JEP 193 enhanced volatiles is safe performant enhanced atomic access to fields and array elements. That's what it's scoped at. And what we would like to do is replace nearly all usages of unsafe in Java util concurrent. If we can do that and get the performance and get the API, I think we can give a big tick and say, yes, we've reached our success here. And it depends on JEP 188, the update of the Java memory model that's ongoing discussions, some very heavy discussions in there ongoing, which is sort of above my head somewhat in some cases, but there's some movement going on there, but there's going to be some enhancements to there to say what a compare and set means and stuff like that in actual Java memory model. So I said the success metrics. What we do if we design an API, it should be at least as good as unsafe, and obviously performance should be almost, or as close to as unsafe as possible, but definitely faster, better performance, better dynamic overhead than the atomic star classes we have existing in today. So this is a Strawman proposal we have on the JEP. And what we proposed was to have this special volatile syntax on a field. So if we have a volatile int count, and we want to sort of do an atomic increment and get, we could call count.volatile increment and get, and that's a Strawman. How many people like that? Do you like that? Does it look a bit strange? Stuart likes that one. Well, this is the best we came up with, and it seemed okay, but it's kind of weird because count.volatile wouldn't evaluate to anything. It would just throw an error if you did that. It doesn't return anything. So there's this sort of, this int looks like it has a secret field called volatile there, and it returns a secret sort of floating interface around with these things on, and I'm thinking, it seemed a good idea at the time, but it's a Strawman, so we can burn it down. It requires language changes, so we need some special compiler tweaks to say what this actually means under the covers in bytecode. We need to compile it down. But what should the implementation be for that? And would that implementation be sufficient just on its own? And this is the question I'm getting to. Is there a way to do this without making such strange language changes? Can we do it a better way using the existing classes and stuff like this we have in Java and hotspot and Java-C and stuff without having to do this strange sort of slight trick with the language changes? And this is where I'm getting into alternative proposals of what could be this implementation technology for the JEP, and essentially, are these sufficient on their own without having to do these language tweaks for the moment? So method handles. So method handle is a reference to an unlining method, but it can also be reference to a constructor or a field, if you like. It doesn't have to be directly to a method. And surprisingly, if you look at the method handle code, which I'll show in a moment, you can get access to fields, a volatile access to fields, and it inlines surprisingly well, as I'll show. And with some tweaks, you can actually support other forms of access, like compare and set, stuff like this. You can just tweak the method handle code quite easily underneath the covers to do that. So when I was looking at method handle codes, I thought method handle codes was quite cunning. As Lambda forms and method handles yesterday was a whipping boy, it seemed to me. Well, I was thinking, no, I think these things are quite cunning. When I think of cunning things, I think of Blackadder. Anyone a fan of Blackadder? It's like, so when I saw this, I thought it was a cunning plan. You put a tail on it, you could call it a weasel. I really liked it. I thought it upped a lot of Java code, upped a lot of stuff into the Java land, and it was so much easier to maintain and iterate on with Lambda forms. They have some issues, but I think we can iterate a lot faster in Java land with a couple of key intrinsics going on in hotspot around method linking. And so my hope is VarHandles are cunning too, but I'd say perhaps they're marching with ill-deserved confidence in the general direction of this presentation. That's a play on another quote in Blackadder if you actually go look it up. So I'm going to destruct method handles. I'm going to do it in a particular way that sets the stage for VarHandles, and there's a link on the wiki here which describes what I'm going to talk about here. So I'm going to go into IntelliJ, and let's get some code up there. So I'm going to zoom in so you can actually see this, but I'm going to do a little experiment here and show some method handle code. So I've got a receiver class here, and I've got a volatile field string called vfield on there. And what I'm going to do is create two method handles for this. One is a setter, getter, and one is a setter. And these are direct method. I'm looking up direct method handles to this volatile field. This is why IntelliJ is saying this field is not used, because it doesn't know that these method handles will access this field. And then I'm going to have two methods, set and get. I'm going to call these method handles with invoke exact. And you have to wrap around a throwable because the invoke and invoke exact throw throwable, so you have to deal with that. But if we just look at the invoke exact here, we see, well, it's got this strange annotation on it called that polymorphic signature. And it's an object, turns an object, and it has a bunch of objects as arguments. That's pretty general stuff. But let's have a look at the bytecode of what this actually compiles down to. Notice here in the get value, I'm having to do an actual cast to string. So it's not an object, it's a string. So what happens when we do bytecode? Is this going to get erased, or is it going to do something a bit different? So I just run the Java P here, on here in my terminal window. I'll zoom in, show it. So let's have a look at the bytecode of the set method that I'm going to focus on. So here's the set value. And we have an invoke virtual on the invoke exact. But what we're getting is we're getting the actual types I'm passing in. We're not getting the objects. So we're actually sort of capsulating at the call site the types we're dealing with. So we have the receiver and we have the string of value here. OK, so what happens if we actually run this? So I've got a main method here, and I'm calling set value a bunch of times, number of times. What I'm doing is I'm calling it the first time to get it linked, calling it a bunch of times to get Lambda forms compiled, then I'm calling it a bunch of times to get it all nicely compiled in C2, and then I'm calling it again. So let's see what the inlining trace of that is. Oops. OK, so I ran that, and we get a lovely inlining trace. This inlines perfectly. So we see a call to set value here. We see a strange-looking number there, a Lambda form. It's spun up a class. We doing some work. I'll go into that in a bit. And then we see another Lambda form here that's actually doing some more work, but it's more specific what we want to do. And at the end of all this, we get a put object volatile, which is our volatile right at the bottom. So all this, bump at the bottom there. Now, in terms of assembly code, what do you think the assembly code will be for that? Will it be really big? Will it be really small, medium? Do you think there's loads going to be generated? How many people think a lot of assembly code will be generated? Pardon? That's not the answer I wanted. But, okay, I'll show it here, okay. Let's run this. Okay, so I just put it into Vi. So this is just one run, but it looks almost the same in every run for me. And so let's go back up here, let's zoom in. So we got two arguments here, RSI for the receiver, and so registers RDX for the string coming in as parameters. And let's scroll down there. So this is interesting. We're comparing the value to null. And we're saying if it's null, we're going to break out and do something else instead. We're getting the reference to the address of the field. Here we're storing the field here, and there's the compressed stuff going on here, I think. And then we're doing a card mark, and then we're doing a store load at the bottom there. And then there's a little bit of bookkeeping, and then we return. So all that inlining went compressed all the way down to those set of instructions. And that's almost as much as you get when using unsafe directly. So we had all this inlining going on, but unsafe, the hotspot can see through it because those method handles were constant folders. So all it held was constant folder 2, and we get down. And this was the key to me to think, method handles could be a solution to our problem here. What we have is the safety checks performed by method handles, and most of these checks can be optimized away or optimized for the point of simple sort of test jump instructions. In actual fact, this test instruction here annoys me because it shouldn't exist. We should be able to optimize that one away too, because our receiver is this. We don't need to check it for null. Why are we checking null for a value? We don't care if it's null or not, so why is it there? So we can even optimize it further, and it's almost the same code as unsafe down at the bottom when you're comparing it. So let's actually debug this now. So I'm going to set up, let me just check my debug points are correct, yes. So let's run this. I'm going to debug at the first point here. So this is my first call that I'm going to do, and I'm going to step into it. I'm going to step into the invoke exact here, and let's see what happens. Did I actually do it? Oh. Well, that invoke exact is a final native method, so it popped down into the VM. The VM said, I don't know how to link this. I'm going to pop it back up to Java. I'm going to call a method which will tell me what to do with this linkage, with this call site. So it's like a low-level version of invoke dynamic, if you like. And this method, actually, it will return a member name which characterizes the method to link to. It's like a shared thing between the Java and the VM, which says, you link to me. I'm going to call you once, and you link to me. And it actually returns two values. So what John was saying, there's a pain point here. We actually return the method we want to link to, and we return any arguments we want to append to this when we call it. So it's actually returning two things. I'll show that in a moment. So if we had tuples, we could return it all in one go rather than having to do this pain of sticking extra things we want to return in an array. So let's continue all the way through. So now I'm going to continue all the way through. We've got a bunch of other calls to this invoke exact, but we don't see any link up call. We only call it once. So once we've linked to it, that's it. And we get it back. Now we can start debugging into this sort of inlining trace here. So let's debug through into here. I'm going to enable some more breakpoints, like so. So the first thing we note here is there's a spun-up class. IntelliJ doesn't know what it is, so we can't debug into it, but we can still actually look at the arguments of this invoke exact call we linked to. And what it has as the arguments here from 4 arguments. The first one is the method handle we're talking about. The second argument is the receiver holding our field. The third argument is the value we want to write to that field. And the fourth argument is the method type that represents our types at the call site. So we appended that argument onto the end when we linked to it. Every time we call this method, we'll append this little structure onto here. And then what happens is, when we do this check here, we check that the arguments, the types at the call site are the same as the types I expect. And it's essentially just a quality check. We have the method type on our method handle, and we have the method type associated with a call site. And if those two are equal, we're good to go. We know we're safe. If they're not equal, we can bomb out and throw a wrong method type exception. That's a very, very fast check, just an equality check. So let's continue along with that. Now we actually link to doing some real work. There's another lambda form generated in that inlining trace, and we see our 3 arguments as before. We drop the fourth argument. We don't need it anymore because we've done this check. And we have a method handle again. If we look in our method handle, we have a form. And in our form, we have a VM entry, which points to the method that I'm actually debugged into right now. So that's the method we're actually linking to. So we're doing some work here. We're getting the field offset that we want to, where is it? We're getting the field offset we want to use with unsafe. We're doing a null check on the receiver. The object passed in here is receiver, like so. And then we're doing a cast to make sure that the object we pass in, the value, is actually of the type that we expect. And the cast will be the field type here, which is of string. Now, this isn't a safety check. We already know we're safe because we did the method type checking before. This is to tell the profiler that I've got an interesting type here that you should know about. And this is a thing which is leaving null pointer check droppings around. It's not fully optimizing the way, because I think the type profiling says you're an interesting type. If you're null or not null, I'm going to record that bit too. What we really want is just say the type. We don't care about null. Usually these will get hoisted up, though. OK, we do some more work here. Let me just set the breakpoint there. And eventually, we do the check cast. Eventually, we get to the put object volatile here, and that's actually where we do our write work. But all that gets nicely in line. So hopefully, that will give you an indication of the sort of process that's going on here in direct method handle calls. It's, as I said, it's written down in that document. You can look at it more carefully there, and it's very easy to debug and test this yourself to see what's going on. I find that process interesting. There's essentially 2 steps. First step does some type checking. The second step does the actual work. And those 2 things are interesting. So just to recap, the method handle invocation is signature polymorphic. We can pass any types we want in, but we save those at the call site. And a method handle has a method type descriptor that we compare with that at the call site. And it also has a lambda form that holds the method we actually want to call, want to invoke. So it's like double linking, double dispatch in a sense. So let's have a look at some code in the fork join pool that's currently using unsafe. I'll actually look at it for real here rather than on slideware, because you see better syntax highlighting. So here's an example of using unsafe in Java using this poll method on the fork join work queue. So we see a bunch of unsafe calls here. The first call we see is a get object volatile here. So what this is doing, it's doing a volatile get on an array element. So what we want is here's my index here, and we're shifting it and adding to get the index into the array. And essentially what we're doing is Doug has been very careful here to make sure that the index never goes out of bounds, so we never read some crazy value and start segvying and stuff like this. This is one reason why we do this. The index will go over the bounds of the array, so we basically mask it by array length -1 because the array is a power of 2. So we get object volatile. We check if it's not null. If it's not null, we swap it with null, compare and set, compare and swap. And then if that succeeds, then we update the lazy set of an integer by 1. And if it's null, or if we can't compare and swap, we repeat in a loop. And this is quite common in compare and swap. What you often do is you go in a loop. And if the performance of this isn't very good, if there's any delays here that slow things down, your aggregate performance tends to slow down, even if there's small delays in here, because there'll be lots of spinning going on. So that's fairly easy to understand. This is annoying, the shift and base. This is kind of annoying too, but it's reasonably readable code. So theoretically, I modified this to what it might look like if you're using method handles. If you remember in the code I showed, I had to catch throwable. So I'm not trying to work out how to modify this code to catch throwable. I just put it up onto method, which is probably not what you want to do. But you have to deal with throwable now if you're using method handle with invoke exact, which is not a good thing. Good thing is this shift and addition goes away with your index for j. We still have to cast on the return type. We have to name our method handles appropriately so it's readable because they're all invoke exacts. And also we have to cast the compare and set method handle, if it existed, to Boolean there in the if statements there. And I modified fork join code to update it using a basic version of VarHandles where I had to do all this casting. And it's ugly code just to even do compare and set with Booleans and that. It's pretty painful. So I think API-wise, it's actually got negative across. It's not as good as unsafe. We're not doing so good there. The performance is good. The inlining I showed there, it actually works in larger context. What I didn't show in that code I forgot to show is that you notice all these @force inline annotations in the code and method handles which force the inlining, so it ignores inlining limits and stuff like that to make sure it all gets noticed by hotspot. So the performance is actually good. It's close to unsafe and faster than atomic. But I think we can do better. And this is where VarHandle comes in. So it's an abstraction of safe access to a memory location, leveraging method handles, invoke intrinsics, and some misc unsafe. So as Brian said, it's method. You can think of it as method handles for data. We can have one abstract class, and we can have many things supported by this abstract class. So we can have many access modes, one per method. We can have the fenced, atomic, CAS, stuff like this. We can have many access kinds. It could be static, instance field, array, or off heap. And we could have many value kinds too. It could be an object, ref, a primitive, or even a composite value with value types. So I patched langtools and hotspot to support this, and I was very surprised and pleased that I didn't have to make many changes. This is just the change sets here I made to it. And okay, I patched hotspot in a way that it might raise some eyebrows, because I don't know the code very well, but it works for me. The experts need to look at this and say, oh my God, this is the way you do it properly. But I didn't have to make many changes, and it's manageable. I don't have to do some horrible, every time I upgrade hotspot, every time I do a pull to hotspot code, I don't have to panic going, oh, am I going to merge my patch again? It's usually pretty clean, merges on top. And it's the same with Java C as well. I made some tweaks there, and it actually worked out okay. So I think the lesson here is even though these features on method handles are focused in a particular way, they're actually written in a way that's more usable. And I think that's partly by design. So here's VarHandles. Here's what a VarHandle will look like. Let me go into the code instead and show you. So I have a modified version of the JDK here. So here's a VarHandle. So it's got a bunch of methods, each corresponding to an operation you want to do, and each are annotated with a polymorphic signature, so you see the similar patterns to the invoke exact method there. So we have relaxed access, volatile, lazy accessors, and down below here, we have like our compare and set. Now I tweaked Java C, so we don't need to refer to object. So if we know we're Boolean, we don't need to be object and cast it. We can just be Boolean instead. So it's not polymorphic on the signature on the return type, just on the arguments you pass in. So I wrote another document called Deconstructing VarHandles, which follows the same process I did for deconstructing method handles to show how it works. And it's online on the CR Open JDK list there, linked there. So let's actually go in and deconstruct that instead. All right, where's my project? Okay, so here's similar VarHandle code. So again, I have my receiver here. I have a static final VarHandle field, and I look up the VarHandle, give it a receiver class, the name of the field, and a string class, and I look it up. And then I can do a set value, and I can just call field set volatile with the arguments I pass in, same for get, and the compare and set, and I don't need to do any nasty casting as before here, and I can go through the same process as before and debug this. So let's just debug. Actually, no. First of all, let's just show that it actually works. So Java P. Let's look at the compare and set. So here's the invoke virtual for compare and set. So we're seeing we're passing in the arguments we want. It's not all objects. So actually, it's good at the call site, receiver string, and it returns, should return Z. There at the back, yes, that. Like so. Now, does this inline? Let's run it. Yes, it does. So this is my compare and set method I'm calling above. This is our compare and set we're calling. It links to something like a bunch of static methods I call on VarHandle guards, which I pre-generated. It calls the check exact, a bit like on method handles. Say, are the types okay? If they are, great, let's continue. Then it calls compare and set on a field instance ref handle that does the actual work, does the null check, does the cast reference on the value we want to set, and then calls unsafe compare and swap object underneath the covers. Like that. So very, very similar pattern to what's going on invoke exact here. And just to make sure that we're all right here, assembly code. So let's go scroll down here. Again, we see our test for a value, which really shouldn't be there, but it is. And then we see our lock for compare and set, and then we see a card mark write, and a bit of bookkeeping, and then return. So again, all that thing just boom, compressed all the way down to that level of machine code. It seems quite diverse in a way. We do all this work, and then we undo all the work and put it in machine code, but that's the way it works. Okay. So let's debug that to show it works in the same way. I'll remove a debug point. I don't know why you're doing that. I'll stop it and try again. Okay. Doesn't work the second time, I'll stop. So we're at the debug point there. I want to just show you that it actually does go in the up call. So we get the up call again. You can see what the caller class is, and we got the type here, which is the, where is it? The type here should be the method type, if I can actually print it out. So a method type is receiver string Boolean. This is the type we're checking against. Like so. Let's continue running that one. So no linking anymore when we got down to the bottom. And let's actually debug into that. So I've wired things up explicitly. I haven't used Lambda forms at all. I'm using the low-level mechanisms to wire up VM and wire up the linking with the VM and Java. So I'm not generating any code or anything like that. And one reason was because I knew the Lambda form code was changing, and I knew that if I tried to monkey around with that, I'd have to keep updating my patches. So I just wanted to isolate myself and keep it simple. It makes it easier for me to debug as well. So here I pre-generated these methods. I wrote a little code to pre-generate all these methods for the shapes I wanted. So we see this force inline here. We're saying, hotspot, I definitely want you to inline this. And this is a generic check method, essentially, for our compare and set. And it takes my VarHandle, base VarHandle, and then everything's erased in a polymorphic signature. You erase things to objects and widen, so like a Boolean to int, stuff like that. So we do the type check here, like so. And then we actually call something called link to static. And this is actually our second linking step. So once we've done our type check, we can drop the last argument, and we can pass all the arguments and put another argument on the end of it, which is the actual method we want to link to do the compare and swap operation. So internally, the VarHandle has a var form, which contains all the things I need to link to for the operations I need to do. So if we debug that, go in there, we actually get down to work that we need to do, and we do our null check, and we do our unsafe compare and swap, getting the access to the field offset, and then casting the reference and so forth like that. So you see a very similar pattern here. I've just done it explicitly, no code generation or nothing like that. So there's no churn spinning up classes or anything like that. Okay. So that basically summarizes what I just showed you there. So in terms of the fork join pool, is it any better? I show the code instead. So where is it? Here we go. So this is my modified. I modified the whole of fork join and some other Java util concurrent classes so I can performance test it. But here is the VarHandle code for the same method as before. So again, we don't need to do the shifting and stuff like this. We do the get volatile for the array. We do the compare and set. We still need to cast. If you just have null in there, what type should it be? We'll choose void. What else can it be? Void is the no type, I guess. Can't be any other type. It's a shame, but that's the way it goes. And then we do set release on the integer here. This, I think, is on a par or better. We don't need to do this shifting and adding here, but we still need to do a cast for null here. So I think it's actually, I'm biased, but I think it's better. So. Okay, so here's some performance numbers. They're in this document, far more detailed than here. But I wanted to show what you do if you compare unsafe with VarHandle, with reflection, atomic reference field updater. So unsafe is about as fast as VarHandle when doing a volatile set and get a nano benchmark. Field reflection is very slow. It's on a par with bytecode's get and put field. It's also on a par with the atomic field reference updater if I use the exact types. If the types I set up to construct it with, and I pass an instance of that exact type, it boils down to the same time. If I pass subtypes, instances of subtypes instead, it gets slower. But there's something going on underneath the covers, and I think this is what Sergey gets down to active benchmarking. You have to look under the covers what's going on. That doesn't make sense to me. When I looked at using JMH with the excellent profile, perf profile, and perfasm profile, it actually shows that atomic reference field updater runs more instructions per cycle than unsafe. It's the store load barriers getting in the way of understanding what's going on in terms of measurements. So we see there's more instructions run. If we look at the actual code here, this is my generated code using JMH and the Linux perf to get the hotspot thing. JMH will annotate my assembly code with the percentage of time approximately taken for the instructions and cycles, which is an excellent, excellent utility to work out benchmarking. So you see this, the store load barrier here I showed you before. We see most of the time it's taken around that store load barrier, but if we look at the generated code for the reference field updater, we see, oh, it keeps going and going. There's a lot more code generated there, so we know that we're not as efficient as atomic reference field data in this case. Okay, so if I remove the store load barrier and just do a release set or a lazy set when a volatile get, we start to see what's going on under the covers better. So if we remove that store load, we see that VarHandle is slightly slower than unsafe, and we see that the atomic reference field data is slower than exact types and even slower when using the subtypes. So that gives us a better reflection of what the execution is going on underneath the covers. And I think this, the difference between unsafe and VarHandle is due to the null checks. And here's a benchmark for compare and swap or compare and set, which have unsafe and VarHandle are virtually the same, whereas the atomic reference field data is slower. So I think this gives me 2 ticks. The API should be at least as good as unsafe, preferably better. I think it's all right. Performance results, I think, are looking very good so far. The nano benchmark performance results and some other results I've done are looking very, very good. It's all inlining as I'd expect. It's all, we're not getting any major anomalies. There's a couple, but I think we can fix them. I don't have time to go into it too much now. But there are some negatives. There's no static type checking. If I can pass in any types to this invoke exact, I'll get a runtime exception. The cast to null kind of annoy me. The casts are required for a return value type, but Maurizio says he can solve that problem by using better type inference. So that's good. So there's another way here. I thought, well, what happens if we have one interface per access kind shape? So if we have a concept like a field handle or an array handle, and we refer to the type variables in the polymorphic signature here, can we get that to work instead? So the question is, what about primitive types? We can't represent primitive types in here. Valhalla is not here yet. But what you can do is a rather sneaky trick, a cunning plan. And a box parameter type can be associated with its primitive type of the call site. I can tweak Java-C to say an integer really means int here. And because int can be Java-C knows that int can be inferred integer because it will do automatic boxing and unboxing, you can trick Java-C in just letting it go through. So, and nobody, well, I would say that atomic operations on refs to box type instances are very, very rare. Why would you want to do that? So let me show you an example of that running. Okay, so let's look at field handle here. So we got a field handle instead of a var handle. We're saying it's of a receiver and string, and we can look them up, look up integers or strings like this. So the question is, for this compare and set here, is there going to be boxing going on when I do this? Can we avoid the boxing? Even though we're talking about integer, can we get rid of the box? So if I look at the Java P output here, and just find it in the compare and set, there's a call to compare and set, and there's no boxing going on, it's just integers. So we tweaked the polymorphic signature code. We fooled Java-C into thinking, well, int is integer, which is good, but we don't incur the boxing. Question is this cunning plan too sneaky? We'll have to see. So if we debug into this one here, we're going to have a link up here and get rid of that. So we go to one of these guard methods, which has an object receiver and an int, and a symbolic method type. And when we go down to, and when we link it to our, go back up here, and we link it to the right one to do the compare and swap on int down here. And the same pattern doing the null check there. So no boxing going on at all. So we have a solution for primitives, but it might be a little bit too much sneakiness going on to be something we would support in for a solution for enhanced volatiles. So I'm saying, is it too Weasley? And do we wait for Valhalla instead and support any on here? Who prefers waiting and who prefers not waiting? Anybody? It's kind of one of these balances that's hard because it's useful now, but it could get better in the future. So also I want to show a quick thing here. It's actually possible to point a VarHandle off heap. And I have an implementation of this called VarHandle, which takes the array type receiver, takes the index that you used, takes the values you want to read and write into the array, and you can create an off-heap handle for, say, integer, like so. I can create a byte buffer, direct byte buffer. I can create an off-heap region pointing to that byte buffer, which just extracts out the address. And then I can do a compare and set off-heap using that handle, like so. So that is actually a compare and set, passing in the long index, passing in the here, passing in the value I want. I want to swap it from 0 to integer.max value. And then I want to get it out using long index as well. So we can have huge long index accessible arrays if we want to. And then I can just compare it by getting it out using ints just to make sure that it actually works. This does actually work. I'll run it and prove to you. It should print out the two same values, like so. So it actually is modifying exact same memory address there. Okay. So that was off heap with VarHandle there. Now just proving the point that the memory can be on heap or off heap. So in summary, we can get safe access to a memory location and safe and performant access. There's a couple of things we need to tweak, but actually not that many. We need to look at these null checks. We need to look at, when accessing arrays, whether the bounds checks get hoisted up. We need to do some work there. When C2 kicks in, it looks pretty good. More measurements are required. I've got to get some proper measurements using the 166 loops code, stuff like this. I've done a little bit. It looks promising. There's some API improvements that are possible with some cunning. I'm not sure if it's the right thing to do, whether we should wait till Valhalla comes along and use that instead. But there's some interesting synergies here between Valhalla, between Panama, and Arrays 2.0. So it's kind of interesting, exciting stuff, sort of intersecting all these little things here. And that's it. Any questions? Yes? Can you get the mic? I can't. I haven't got a mic.
How do you handle Indianness with the off-heap?
Yeah, good question. My prototype doesn't at the moment. But actually what I forgot to say was you could, in here, you could say what endiness you want in the handle when you actually create it. And then you could optimize and don't have to do the if check every time you do the access. You could specify the order here too. I forgot to say that. So in my prototype, I don't, because I just knocked it up first. But you can do it here, and it's quite interesting. You can hoist out the checks when you actually do the lookup. Yes?
So when we get tuples, how do I wrap one of these around several accesses to the same tuple?
So you want to atomically update a tuple. Yes, this is a connection with value types and Valhalla. So we got to make this work with value types as well, and we got to work out efficient ways of atomically updating that data structure. If it's small, there might be some two cas type instructions. If it's larger, we might have to resort to locks. There's various techniques we could probably do there. We have to investigate. That's it. I'm between you and lunch and the Java memory model. So, okay, thank you.